Let's say I've got an m by n matrix A. That's my matrix right there. And I could just write it as a series of n column vectors. So it could be A1, A2, all the way to AN. Now let's say that I have some other vector B. Let's say B is a member of the column space of A. And remember, the column space is just a set of all of the vectors that can be represented as a linear combination of the columns of A. So that means that B can be represented as a linear combination of the columns of A. So I'll just write the constant factors as x1 times A1 plus x2 times, that was A1, plus x2 times A2, all the way to plus xn times an, where x1, x2, xn, they're all just arbitrary real numbers. Or that another way to state this is that means that A, which I could write as A1, A2, all the way to AN, times some vector x1, x2, all the way to xn, is equal to B. These two statements are equivalent. We know that B is a member of the column space. That means that B can be represented as a linear combination of the columns of A. And then this statement right here can be rewritten this way. So you can write that the equation AX equals B has at least one solution X that is a member of Rn. And the entries of X would represent the weights on the column vectors of A to get your linear combination B. This is all a bit of review. Now, let's draw Rn. Any solution to this equation right here is going to be a member of Rn. Remember, this was an m by n matrix. We had n columns. So this has to be a member of Rn right there. So let's draw Rn. So Rn maybe looks like that. So that is Rn. And let's look at some of the subspaces that we have in Rn. We have the null space. That's going to be in Rn. The null space is all of the solutions to the equation Ax is equal to 0. That's going to be in Rn. It's all of the x's that satisfy that equation. So let me draw that right here. So let's say I have the null space right there. So that is the null space of A. And then what else do we have in Rn? Well, we have the orthogonal complement of the null space of A. Let me draw that. So we have the orthogonal complement. Let me do that in a different color. We have the orthogonal complement of the null space of A. So the orthogonal complement of the null space of A, which we could also call, we learned this in the last video, this is also going to be equal to the row space of A. The row space of A, which is also just the column space, the row space of A. The row space of A is the column space of A transpose. So we have two spaces here. That is the row space of A. So I have two subsets of Rn. I have the null space, and then I have the null space's complement, orthogonal complement, which is the row space of A. Now, we've seen in several videos now, and I proved it, I think, 2 videos ago, that any vector in Rn can be represented as a sum of a member of our null space. Let's call that vector n. And let's say some vector in our row space. Let's call that vector r. Any vector in Rn can be represented as a sum of some vector in our null space and some vector in our row space. So any solution to this equation is a member of Rn. So it must be able to be represented by some member of our null space and some member of our row space. So let's write that down. So let's say x is a solution. So let's say that x is a solution to Ax equals b, which also means that x is a member of Rn. X is a member of Rn, or x is a member. So because it's a member of Rn, we can represent it as a combination of one vector here and one vector there. So let's say that let's say that x is equal to some vector r, let's call it r naught, plus n naught, where r naught is a member of our row space, and n naught is a member of the row space's orthogonal complement. They're their orthogonal complement of each other. So n naught is a member of our null space. Fair enough. Now, one thing we might wonder is, clearly this vector isn't a solution to ax equals b. This vector is a solution to ax is equal to 0. But we might be curious as to whether this solution right here, this member of our row space, is a solution to ax is equal to b. This is kind of what we're focused on in this. So let's solve for r naught right here. So if we solve for r naught, if we subtract n naught from both sides, we get r naught is equal to x minus n naught. All I did is subtract n naught from both sides, and then I switched things around. I solved for r naught. Now, if we multiply a times r naught is equal to a times this whole thing. Let me switch colors. That's equal to a times x naught minus n naught, which is equal to ax minus a. Let me write it down. That minus looks a little. Let me write minus a n naught. And what is this equal to? Well, a times x, we already said that x is a solution to ax equals b. So this right here is going to be equal to b. And n naught is a member of our null space, which means it satisfies this solution right here, that a times any member of our null space is going to be equal to the 0 vector. So that's going to be equal to the 0 vector. So you have the vector b minus the 0 vector, and you're just going to have the vector b. So we just found out that a times this member of our row space, let's call that r naught, that's that guy right there maybe, a times r naught is equal to b. So this is a solution. So r naught is a solution to ax is equal to b. So far, it's kind of an interesting result that we have already. If you give me any vector here, b, that is a member of our column space, right? Then there is going to be some member of our row space. There's going to be some member of our row space right here that is a solution to ax is equal to b. Now, the next question you might wonder is this the only guy in our row space that is a solution to ax is equal to b? And to prove that, let's assume that there's another guy here. Let's say that R1 is a member of our row space and a solution to ax is equal to b. Now, the row space is a valid subspace. So if I take the sum or the difference of any two vectors in the row space, I'll get another member of the row space. That's one of the requirements for being a valid subspace. So let's see this. So if I take two members of our subspace, so if I take R1 minus R naught and I take their difference, which is just the sum of, it's a sum, well, you multiply one times the negative, and that has to be a member of the subspace, and then you're summing them. So this has to be a member of our subspace. So this must also be a member of our row space. That's because our row space is a valid subspace. You get two of its members, you take its difference, that also has to be a member. Fair enough. Now, let's see what happens when you multiply this guy by a. So if I take a times R1 minus R naught, what do I get? I get a times R1 minus a times R naught. We already figured out, or for R1, we assumed that it is a solution to ax is equal to b. And R naught, we already found out it is a solution to ax is equal to b. So either of these, when you multiply them by a, it equals b. So this equals b, and that equals b. So you get b minus b, which is the 0 vector. Now, this is interesting. This tells us that r minus r naught is a solution to the equation ax is equal to 0, right? When I put r1 minus r0 in the place of x right there, and I multiplied it times the a, I got 0. I got 0, which implies that r1 minus r0, that this vector is a member of our null space. So I have a vector here that's a member of my row space. It's a member of my row space. And we got that from the fact that both of these are are members of our row space, and the row space is closed under addition and subtraction. And the vector r1 minus r0 is a member of my null space. And we've seen this several times already. If I have a vector that is in a subspace, and it's also in the orthogonal complement of the subspace, right? The null space is also the orthogonal complement of the row space, then the only possible vector that can be is the 0 vector. That's the only vector that's inside of a subspace and its orthogonal complement, or a subspace and its orthogonal complement. These two guys are the orthogonal complement of each other. We drew it up here. So we get that r1 minus r0 must be equal to the 0 vector. That's the only vector that's in a subspace and its orthogonal complement, which implies that r1 must be equal to r0. When we take the difference, we get the 0 vector. So we have a couple of neat results here. If I have some, what do we know so far? We know that if we have some vector b that is a member of our column space of A, then there exists a unique member, right? We just proved the uniqueness. There exists a unique member of the row space of A, let me do it in a different color, of the row space of A. So this is the row space of A, such that, a unique member of the row space of A, let me call that R0. Let me do that in a different color. I want to make this really stand out in your brain. R0. So we know that R0 is a member of the row space of A, such that R0, let me write it this way, R0 is a solution to AX is equal to B, which is it's a little bit of a complex statement here, but it's interesting. You give me any B that's a member of the column space of A, then there will exist a unique member of the row space of A. That's my unique member of the row space of A. That is a solution to AX is equal to B. Now, we can go further with this. We wrote up here that any solution to this equation, ax is equal to b, can be written as a sum of r0 plus n0, where r0 is a member of our row space and n0 is a member of our null space. And that's because we have a subspace and its orthogonal complement. So any member of Rn can be represented as a sum of a member of a subspace and a member of the subspace's orthogonal complement. So let me rewrite that down here. So we already said that any solution x to ax is equal to b can be written as a combination. Let me write it this way, as a combination of r0 plus n0. Fair enough. Now, what happens if I were to what happens if I wanted to take the square of the length of x on both sides of that? So let me write this down, and you'll see why I'm writing this, because I have another interesting result to show you. So if I were to take the square of any solution to this equation right here, right? Any solution to that equation right there, well, that's going to be the same thing as x dot x, which is the same thing as this thing dot itself. Same thing as r0 plus n0 dot r0 plus n0. And what is this equal to? this is equal to r naught dot r naught, r naught dot r naught, plus n naught dot r naught, plus n naught dot r naught, plus n naught dot r naught again, plus n naught dot r naught again, plus n naught dot n naught, n naught dot n naught. I just kind of foiled it out, and we can do that because we know the dot product exhibits the distributive property. So this thing right here is equal to the length of r naught squared. Now that we're going to have plus, well, what is n naught dot r naught? What is n naught dot r naught? We don't even have to simplify this much more. N naught is a member of our null space. R naught is a member of our row space. Each of them is in a subspace that is the orthogonal complement of the other, which means that everything here dotted with anything in here is equal to 0. So r naught dot n naught is going to be equal to 0. These guys are orthogonal to each other. So that's going to be equal to 0. That's going to be equal to 0. And then you get plus, what's this? N naught dot n naught is just the length of the vector n naught squared. These are all vectors. And so we get the length of the vector x squared. The length of the vector x squared is equal to the length of our member of our row space squared, our unique member of our row space squared, plus that member of our null space squared. Now, this is definitely going to be a positive number. That's definitely, it's at minimum 0, but it has to be something larger than 0. So we can say that this quantity right here is definitely greater than or equal to just r naught squared. Or another way to think about it is, you give me any solution. You give me any solution to the equation ax is equal to b, and the square of its length is going to be greater than or equal to the square of r naught's length. Or, since both of the lengths are always positive, you can take the kind of the positive square root, and you won't have to switch signs there. That the length of any solution to ax equals b is going to be greater than or equal to the length of r naught. So that makes r naught kind of a special solution. So now let's write our entire statement, everything that we've learned in this video. So if B is a member of the column space of A, then there exists a unique R naught that is a member of the row space of A, such that R naught is a solution to ax is equal to b. And not only is it a solution, it's a special solution. R naught is the solution with the least, or no solution has a smaller length than R naught. Let me write it that way. Maybe some other solution could be equal. Could have the same length. So, and no solution can have no other solution can have a smaller length. Maybe we could write that if you give me any vector b that's a member of the column space of A, then there exists a unique member of the row space, that is essentially the smallest solution. We could write small as having the least length to ax is equal to b, which is a pretty neat outcome. In the next video, we'll explore this a little bit more visually.